send a little overview on our research network on quantum repeaters. And let me start with the setting. We're all interested in long-range quantum communication over large distances. And probably all of you have seen this fantastic endeavor that people in China have put together, this 2,000 kilometers of fiber network ranging from Shanghai down here up to Beijing up there, and extended by a satellite link over another 2,600 kilometers. So this is probably the longest network that has been realized so far. However, we would not consider this a quantum network. No, correct? Okay, wonderful, wonderful. Okay, so we would probably not consider this a quantum network, but it's a concatenation of individual links. Yeah, and this is called a network of trusted node because at each endpoint, quantum information is converted back to classical information. And to continue, you have to convert then the classical information to quantum and so on. And every time you go from quantum to classical, this could be considered a security risk. Yes? And this is why you need trusted or probably fortified nodes. The other option, and this is what we are interested in, is the notion of a quantum repeater, where you follow a different route. You try to distribute entangled state between widely separated communication partners, and then use these entangled state as a resource for quantum communication. So we have here like an abstract picture of such a quantum network. And what I'm going to show you is that you can have both like linear networks where you try to create and distribute entanglement, but you can also have more complex topologies where you can create multipartite entangled states. A quantum network is not only restricted to applications in quantum communication, but this is also can be seen as an interface for quantum computers. Yeah? So if you imagine that you have quantum computers at different places and you want to switch them together to have like distributed quantum computing, then you need an end-to-end quantum connection between these devices. Yeah? You cannot afford going to classical information somewhere in between. Yeah? Same argument holds true for networks of quantum sensors. Typical physical systems that are considered for the realization of such quantum networks are single trapped atoms, trapped ions, color centers in diamond, atomic ensembles, rare earth, ion, doped solids, and quantum dots. And in our network, we cover these four. And we will hear today about the individual hardware systems in talks by Tim van Leent and John Finlay and Alexander Kubanek and Peter van Loock. So what is our goal? We like to demonstrate some elementary quantum repeater link. And elementary means really we're starting from scratch. Yeah, this is a bottom-up approach where we try to assemble piece by piece the individual constituents of such a network. And of course, in the end, we want to demonstrate some physical secure communication, and we want to do this beyond the trusted node model. That what we have to show first is that there are some quantum repeater advantages. That means that such a quantum repeater gives you the option of having lower losses than a point-to-point connection. And the typical graph that we always show is that blue line here. This is a classical point-to-point connection, yeah, and we plot a relative rate versus a distance, and this goes down over distance just due to the typical attenuation of a signal in a communication channel. Yeah, for a fiber, this is absorption and scattering losses, for example. And a repeater promises to have a connection with a much weaker slope, and the reason is that we try to divide our distance into shorter segments, yeah, where the photons only have to travel shorter distances and the losses are smaller, and that's we can have better rates. And I also already mentioned this, everything that we do is heading towards fiber-based approaches, so no free space or satellite communications here. So building stuff from scratch means we have to demonstrate some very functional units. And the first one we call a quantum repeater segment. This is so-called entanglement distribution. And it starts with local quantum memories. These are depicted in a graphical language here as the blue dots. Yeah, this is a memory. Each of these memories can emit a photon. This is the white dot, white circle here. And this photon is entangled with some internal degree of freedom of this memory, for example, a spin state. And we do this on both sides and send the photons to a central station. And this little box here denotes a beam splitter and a Bell state measurement. That is a measurement of the common properties of the two particles that arrive there. We don't know about the individual states, but we learn about the common properties. And this Bell state measurement projects now the two quantum memories on the outside into an entangled state. And this is in a way scalable. We again start with that entanglement of memories and photons. We do the Bell state measurement. We have, this is called an entanglement swapping operation. And we can concatenate these steps. So we again start here with the local entanglement between memories and photons. We do Bell state measurements at two sides now. We do the entanglement swapping and have now the memories entangled. But now we see, in order to go further, we need to do an operation on the memories. Yeah? And again, you could send out photons here and do some local measurement, but you can also do a quantum gate on these memories to do another entanglement swapping step and to distribute the entanglement now further outwards to the communication partners. And this is more or less the second element that one has to demonstrate. We call it a quantum repeater cell. And it's based on some proposal by Norbert Lütgenhaus called the single sequential quantum repeater. We again have our quantum memories here. Now we do again the spin photon entanglement. We send a photon out to a communication partner, Alice, here on the left side. And she is registering or measuring that the state of the photon in some scheme, for example, a BB84 scheme. And we can repeat this process until success. That means until Alice signals that she has detected a photon. Next step is then Bob does the same, or the second memory does the same, sending a photon to Bob. And these processes, they can run simultaneously, but they don't have to. Yeah? So in principle, this is an asynchronous scheme. Yeah? And after Bob has signaled that he has received a photon, we do again a Bell state measurement on the memories that in general is a quantum gate on the memories. And this quantum gate, or the result of that quantum gate, can be used by Bob to either do some conditional bit flip on that measured photon. And this results in some effective entanglement swapping. Where's the advantage now? If we now assemble these two parts, we have the segment, we have the cell in the center here, we have another segment on the right side. And if we look at the individual constituents again and look at the quantum repeater segment. So the idea was to divide our link into shorter segments where the photons have to travel shorter distances and get lower losses in the channel. So instead of having a channel loss of eta naught, this is a probability that a photon or a bit is produced per mode per channel use. We only have a scaling with the square root of eta naught. So this is okay. Yeah, we have less losses. However, these two photons have to meet at the central beam splitter. Yeah, it's a coincidence is required. That means we have to rely on the chance that both communication attempts from both sides are successful. So we have to multiply the probabilities of success, and we're back to that eta naught scaling. Yeah? So we did not win anything, yeah, in terms of losses and a better slope for the for the point-to-point link here. However, we need this. Yeah, we need this segment to bridge a distance. The second option, however, that cell, this gives us the advantage. Again, both photons have to travel only half the distance, loss the scale with the square root of eta naught. But now the scheme is asynchronous. Yeah, that means that we do not have to rely on a coincidence. And now we add up these scalings with the square root, and this still scales with the square root. So we have a quadratic gain now over the direct transmission. And the secret at this point is that we have a memory, and this memory stores correlations. Yeah? And these correlations enable the advantage. What have we done so far? We have demonstrated in our consortium these elementary schemes. So we have a quantum repeater segment. This has been done in Harald Weinfurter's group, and Tim van Leend will give us details, I'm pretty sure, in his presentation later on. So in very brief, we have rubidium, trapped rubidium atoms. We collect the photons. They emit photons that are entangled with some hyperfine state. These photons are at 780 nanometers, which is heavily absorbed in optical fibers. So we have to translate the frequency into the telecom bands where photons suffer much lower losses in a fiber. This is done with a quantum frequency converter. Then the photons travel up to like 16 kilometers. There's an identical setup in a different location at a different room of university. So two nodes, both of rubidium atoms, connected by, in total, 33 kilometers of fiber. And in the center, we have that beam splitter. Here's the beam splitter where the two photons meet and where you can do the entanglement swapping operation by a measurement of that joint state. And you can see here, this is the fidelity, the blue data points. This is the fidelity of the created atom-atom entanglement, and this ranges from something like something between 80 and 90% for short distances, and going down to a little bit above 60% for this 33 kilometers. The reason for this reduced fidelity being mainly the decoherence of the atomic quantum memory. There's also been a demonstration of the quantum repeater cells. This has been done in Gerhard Rempe's group. They trap two atoms in a cavity, and then they closely run the scheme, yeah, which I already demonstrated. Yeah, so you start a communication attempt from atom A, you produce a photon that is entangled with atom A, and you send it to Alice, and you repeat the cycle until Alice signals she has received the photon. Then you do the same on Bob's side, but at the same time, you also have to keep your memory coherent. Yeah? So you do some decoupling sequences on the atom A, yeah, to store this information that has been, or this correlation, yeah, of that photon that has been sent to Alice. And if both communication attempts were successful, then they do a Bell state measurement on the two atoms and create some secret key rates. And the important result is that it's a scaling law. Yeah? So we again have this black and gray curve here shows you the scaling of the secret key rate over distance for a direct link. This would correspond to our blue line over here. And this quantum repeater cell scheme shows clearly a much smaller slope. So this shows the principle of the advantage. You see, there's some gap here, and this is due to many inefficiencies, and I have to talk about this. There have been many more demonstrations in our network, and I very briefly go through them. So we have entanglement between spins and telecom photons demonstrated for atoms, and for trapped ions, you can preserve photon entanglement over long fiber distances. With semiconductor quantum dots, people have shown photonic entanglement swapping. Again, with the atomic platforms, there's a realization of random access quantum memory, photon-mediated quantum gates. Also for color centers and diamond, spin photon entanglement has been demonstrated. People have built telecom single photon sources and entangled photon sources. So many of the ingredients that we need have been realized already. We're not alone, of course, and here are some recent results from the international community. One beautiful experiment where people use atomic clouds. This is again rubidium, and you can entangle a photon with a spin wave in such an ensemble. These photons are detected on the two detectors over here. And now you still have that spin wave. The correlation is stored in the spin wave. And now you can read out on demand the spin wave, and you can read it out from the two ensembles at the same time. Yeah. So the first photon detections, this can be again asynchronous, but now you can synchronously read out photons from these memories and have them meet on a beam splitter and do the entanglement swapping operation. Yeah. So again, in retrospective, you do some effective entanglement of photons that have already been detected. Another beautiful example by Jan-Wei Pan's group in Hefei. Again, they have rubidium ensembles. They do again the same scheme. They emit a photon that is entangled with a spin wave in the cloud, and now they do again quantum frequency conversion, send it over some 20 kilometers of fiber, and this is a real fiber in a metropolitan area. Okay. And this is the challenge of the experiment here. And then they do again the frequency conversion, convert it back to the rubidium wavelength and write it into the second memory. Yeah, so a connection between two memories, this would correspond to our segment in a real metropolitan setting. And finally, from Ronald Hansen's group, they have demonstrated a small quantum network made out of 3 NV centers. Every NV center has this purple spin here. This is an electron spin. They use it as a communication qubit. That means you can create a photon that is entangled with that electron spin. And Bob has a second one. He has a memory qubit. And they start out with creating entanglement between Alice and Bob and Charlie. And this is in the very same fashion as I showed you before. Yeah, so this is like the segment. So each NV center emits a photon, and they have a beam splitter in the center. This is here. So you have the diamonds and you have the beam splitter. So it's again always the same scheme. Yeah. So they create entanglement as I mentioned, and then between Alice and the communication bit of Bob and Charlie and the memory bit of Bob. And Bob now has these 2 bits, and he can perform a Bell state measurement on the bits or a gate. And depending on what he does, they can create a GHZ state that is a 3-particle entangled state, or they can do an entanglement swapping and create entanglement between Alice and Charlie, who have never interacted before. Yeah, so these are the, again, very basic elements of some quantum networks. Now, real systems do not show these perfect slopes that I showed you, yeah, but we have some offset, yeah, and this offset is due to inefficiencies and infidelities of state preparation. We have a change of slope at some distance because our memory decoheres over time. And so we only have a limited number of communication attempts before the fidelity of the state is so bad that there's no entanglement anymore. And ultimately, at some point, some noise sets in, for example, detector noise. Yeah? So the question is, can we ever have a chance to build real systems? We did lots of efforts to develop a model, since this is mainly due to Peter van Loog's efforts, and try to keep this model as simple as possible. And we try to identify 3 crucial parameters that we call the link coupling efficiency. This is, if you look again at such a scenario here where you have a single emitter emitting photons, you have to collect these photons, and you need some optics, and then you need to inject the photons into a fiber. Yeah? And all these efficiencies go into what we call the link efficiency. And of course, we consider transmission losses in fibers. Yeah? Then you have a memory coherence time. Yeah? And this reduces over time, and this imposes a cutoff, yeah? Limiting the number of entanglement attempts. And finally, we have a clock rate or a clock time that is required to prepare quantum states. You need some excitation cycle, you need to create the entanglement. All this takes time. We model this for the 3 experimental platforms that we have. So we work on neutral atoms and ions, which show a high level of control, but usually have a small clock rate. Color centers in diamond can have very long coherence times, but it's difficult to collect the photons from the diamond material. Semiconductor quantum dots provide very high clock rates, entangled photon pairs at extremely high rates. However, they have a problem with memories. And so each of these systems has its individual pros and cons, and we can calculate secret key rates as a function of distance and try to play with the parameters. What I would like to point out is that there is some extension of that model, and probably Peter is going to report on this in his presentation, to include fidelities, and these are indeed crucial. So if we look again at our link, then we have different fidelities. We have some preparation fidelity. That means the initial fidelity of creating a spin-photon entangled pair. We have a fidelity for the photonic Bell state measurement, and we have a fidelity for the quantum gate. And we sum up, like for the segment here, to create this entangled state. We call this an initialization fidelity. And so for the total segment, we have F init times F gate times F init. And if you zoom in, then you see that F preparation enters with the 4th power. So you better start with high fidelities from the beginning. For the segment, it's a bit easier. We only have preparation fidelity of spin photon entanglement and the gate fidelity. Now, if we look into our real systems, and this is, for example, a rubidium link, and I took the parameters from the experiment that I showed you before. We have some assumptions. We simplify it and say the Bell state fidelity is the same as the preparation fidelity, and now the initialization, I can't see this anymore, scales with F prep cube, I think, and the total fidelity then scales with the 3rd power of the initialization fidelity. And we plot here the required, we plot in color a secret key rate normalized to the plop bound. This is the bound for the direct point-to-point communication. Black means no secret key, rate 0. So most of the time, there's just no effective rate, because memory decoheres too quickly, for example. And this blue part here means that we have some slight advantage, and you see that there's some minimum fidelity required. These parameters, and I should mention tau clock is does not matter here, because the problem with this scheme is that we need classical communication. So we need a feedback from the Bell state measurements. This needs to signal that this measurement was successful. This needs to signal back to the central memory station. Only you apply only that quantum gate if the 2 Bell state measurements were successful. And this classical communication takes too much time. So 1 kilometer takes 3 microseconds. And so at 100 kilometers, you already exceed this clock time here. Extrapolating carefully parameters that we could achieve in the near future gives hope, that we can go beyond that plop bound. And if you look again at the fidelities, they need to be at minimum 94%. Zooming in again, this means that we need preparation fidelities of larger than 98%. And we can compare this to what we have at the moment. And Tim, please correct me if I'm wrong, but preparation fidelities are on the order of 94% in the best case. And what we plan to achieve is just sufficient. But this is just sufficient to exceed that minimum bound, okay? And so this tells us that we really need to invest in improving these parameters. I mentioned how much time? It's over, isn't it? I started later. Okay, good. I mentioned already the scheme which we call node sense photons, yeah, because each memory produces an entangled photon that is sent to a station, and the success of that Bell state measurement needs to be signaled back. Yeah, this takes time. Yeah, this classical communication takes time. And there's some alternative, and we call this a node receives photon model. Yeah, so you put an entangled photon source in the center between the memories, yeah, and send out entangled particles towards the memories. And at the memory side, you either read it in directly, which is not shown here, or the memory also emits a photon, and you have a local Bell state measurement. But this is just sitting in front of the memory, so communication time can be ignored. And so the advantage would be you don't need to wait for heralding signals. This is good for any scheme that provides high repetition rate entangled photon sources as the semiconductor quantum dots. However, this is not arbitrarily scalable. Again, we use a scheme, and this has been proposed by Kaspar Hoffmann. Is he here? I've seen him last night, but so the idea is to use entangled photon sources on the basis of semiconductor quantum dots and to write these photons into a diamond color center memory. Yeah, this is like a hybrid scheme where you try to combine the advantages of the fast entanglement entangled photon production with a long storage time of a diamond quantum memory. And again, we use some assumptions. This is a simplified version now, where we assume a direct memory write-in. Yeah, so the entangled photons are directly sent to the memory, and we assume that we can perfectly absorb them into the memories, which is not the case, of course. Yeah, so this is overestimating the secret key rates here. We have the same scaling with the initialization fidelity. However, there are less steps involved. Yeah, we only have that one spin photon entanglement step that is required here, and not two of them plus a Bell state measurement like in the other scheme. So again, we have a large black area here, and here it is. I'm talking about your proposal. And so with some near future parameters, we are again in a regime where we can exceed that direct plot bound. Again, looking at the fidelities, there's a minimum fidelity of again 94% required, and Peter might tell us whether this is some universal number. I'm not sure about. And the bounds for the preparation fidelity are slightly better here, 94%, and this is what could be achieved already today. Yeah, but again, this is just the minimum fidelity. Yeah? We can get a factor of 400 above the block bound here, yeah, but we should also be aware of the absolute rates. Yeah? We usually avoid talking about this, and this is a distance of 600 kilometers, and the absolute rate would be 10 to the minus 13. Yeah? This is the success probability of sending a photon through the channel. Yeah? And of course, this is a bad idea, yeah, of having a 600 kilometer long fiber connection with just one segment. Yeah, nobody would do this. Yeah, and so this points towards the need for more segments and more repeaters, more nodes, stations in between. And again, I think Peter will talk about scaling laws of how communication rates scale with the number of repeater stations. Good. Goals and tasks of QR.X are to develop optimized hardware components. Yeah, I've shown you that we obviously need to optimize these. We want to have some compact and mobile setups for nodes. We want to implement fiber testbeds. We want to transit from like first generation quantum repeaters, and this is what I've shown you using memories and entanglement distributions, toward at least protocols for second generation, which also involves quantum error correction, towards some proof of principle experiments on third generations, where you first produce a large photonic entangled states as a resource, and then do measurements and local operations. On the theory side, we need to simulate protocols, develop new protocols, and look how we can embed all this into existing layer structures for communication. And of course, in the end, we want to demonstrate some elementary repeater link. Just very briefly looking at the individual points, optimizing hardware components means we need to optimize materials. Yeah, so this is a view on diamond. Yeah, so here we have an envy center. Yeah, and then there's some trapped charges around. There are dislocations, defects in the diamonds. There are other centers around. Yeah, and these all can trap charges, and this leads to wildly fluctuating emission lines, as you see here. Yeah, and photons from these wildly fluctuating lines will never be able to interfere at the beam splitter. Yeah, because they just can't talk to each other. Yeah, they have different colors. So this means we have to invest into material optimization. Same holds true for the generation of, this is a quantum dot molecule where two quantum dots are stacked on top of each other. And I'm pretty sure John Finlay will tell us about the secrets of that. We need wavelength stabilized lasers. We need fast modulators. We need fast electronics, and lots of stuff has been developed already here. For going into the field, we need mobile cryostats. This is one of the main problems at the moment. Yeah, we need to cool down everything, and we need to get rid of the environmental influences on our qubits. Yeah, and this requires low temperatures. And if you go into the field, then you don't have cooling water. Yeah, you probably don't have the 380 volts power plug, yeah, that you need to drive your compressor. Yeah, so this is something that really, really limits us at the moment. Having these mobile, compact cryostats in a rack with just a wall plug. Yeah, this is what you dream of. We need to improve atom and ion traps. We need to improve photon collection. Yeah, so this is an example of fiber cavities, which now many people use. This is an artist rendering. This is a real picture. These are two crossed fiber cavities. Gerhard Rempe has done such an experiment where a single rubidium or two rubidium atoms are trapped in the center of such a crossed fiber cavity. Yeah, semiconductor people and diamond people are also working on nanophotonic structures like bullseye cavities or photonic crystals. We have to develop compact and mobile setups. Yeah, this is an example from my own lab. Yeah, this is a mobile quantum frequency converter. Yeah, we put that into a fancy box, and this can be moved to an experiment. And we have done this, for example, with the experiment in Munich on the rubidium entanglement. There's another box for an NV experiment in Berlin, and ideas to integrate optics onto a chip performed by Christine Silberhorn's group in Paderborn. We want to implement fiber testbeds. Yeah, there's one already existing in Berlin between Technical University, Heinrich Hertz Institute, and Telecom Labs. There's one in progress in Munich between LMU and down in the city center and the MPQ in Garching, about 20 kilometers. There's one being set up at our own university in Saarbrücken. So here's University of Applied Sciences in downtown. And there's another one in Hanover, between Hanover and the PTB. Yeah, so we're trying to go in the field and try to test all these concepts on really existing fiber links. On the theory side, and I'm not the expert now, we talk about simulation. We need to go to quantitative assessments, like I already showed you, modeling of experimental demonstrators, modeling of larger scale networks, devising new protocols, including error correction, embedding in particular into public network infrastructure. Yeah? And here's an example of, again, like a segment. Yeah, but also there's shown some management and control plane. Yeah, you need timings. Yeah, you need control of these processes, and these have to be integrated into the usual network protocols. Yeah. And ultimately, of course, we would like to demonstrate elementary links and again a collection of different options, trapped atoms, semiconductor quantum dots, and this hybrid scheme with the quantum dot entangled photon source and the diamond memories. Yeah, so in the end, we hope that we can show this quantum repeater advantage in the end. this is the consortium. We have about 38 academic groups at 21 sites. 2 small companies, German Telekom, Fraunhofer, PTB, all working towards these goals. We are happy to have an advisory board members, of which at least one member is here today. And yeah, all these people are working towards the quantum repeater, and I hope I can present more results in an upcoming workshop. Thank you very much.
Okay, thank you, Christoph, for your talk. I think you are one of the few speakers who speak second time in this workshop, so you know this procedure with the questions. And perhaps I skip the first 2 questions. I think your opinion is perhaps still the same, and people can watch the answers in the seminar room, where all videos of last year are displayed, and also the answer of the questions, and there are also test sets. So if you want to test yourself, you can make a test there and watch the videos of the last year. But we have an extra question, because we have this year also 60 live here. And so the new question is, which possibility do you see for quantum technology to contribute to the success of 6G networks?
Okay, I'm definitely not an expert in 5G, 6G, or whatever G. I could only guess at the moment that quantum communication would help in the backbone of such a network. Yeah? So I probably do not have enough fantasy of imagining quantum communication via microwave, yeah, or radio frequency, yeah, as used in a smartphone. Probably there are ideas, but I don't see this on at least on a realistic time scale. Yeah, so the only chance to implement quantum communication would be in the backbones. Yeah, and then it's again the usual schemes that you can replace some of the encrypted communication in the backbone by a quantum link. Yeah, whether this is like a hybrid scheme where you create a quantum key and use it as like a super key for a classical encryption, or whether this is a direct key generation. Again, this is a matter of rate that we can achieve over time.
Yes. Okay, thank you. I think the other questions perhaps we shift to the general discussion later, because we are already 50 minutes too late. Sorry for that, but we can then really in the general panel we can discuss this. Perhaps you keep the questions just, and then Tim perhaps can start now. Thank you very much again for this nice overview. And now we come to the 4 platforms which were already presented by Christoph.